Hello everyone, and welcome to another brand new Webinar Wednesday brought to you by the Concrete Preservation Alliance. Today we are talking about beyond the blueprints and how non-destructive testing can be used to support the load rating of a structure when as-built drawings are not available. This is the first of a three-part series focusing on the use of non-destructive technologies to assess structures. As you all are aware, if you've been to our webinars before, the Concrete Preservation Alliance is a growing coalition of organizations committed to advancing the best practices in the field of concrete preservation and infrastructure renewal. Together, we promote the education and awareness of concrete repair industry standards, new and innovative corrosion prevention technologies, and sustainable construction practices. These are some of our active members, and these are the people that we draw on to be speakers for our Webinar Wednesday series. You can find all of our previous series on our website, wesavestructures.info, as well as any of the future ones in the current non-destructive testing series in that same events area. Also on our website, you can find our environmental impact calculator. This is a tool that we've created that allows you to produce a document that, based off of the volume of concrete you've preserved, show you all the different amounts of resources that have been saved, how many Olympic swimming pools of boiled volumes of water, that energy that has been saved, and all those types of things. And just by putting in a little bit of information, you can get a nice PDF spat out that you can use to promote your sustainable practices. Pratik, who we just mentioned, is our presenter. He is a graduate of Oregon State University, where he earned his Ph.D. in material science. He earned his M.Tech in material science from E.I.T, Kanpur, India, and a B.Tech in metallurgical and material engineering from VNIT, Nagpur, India. He's an expert in the ferrous metallurgy and metallurgy and electrochemical corrosion assessments of metals, with a focus on chloride-induced corrosion of steel and concrete. Pratik is also has experience in non-destructive testing techniques, which he'll be going on today, such as ground-penetrating radar, acoustic testing, impact echo, with extensive knowledge in laboratory corrosion tests, steel metallurgy, and materials engineering. And without further ado, I'll let him take it away.
Thank you, Ben, for that introduction, and I hope everyone can see my screen. And thank you, everyone, for joining today's webinar. And in today's presentation, I'll cover the use of non-destructive testing to load rate the bridges, which will include the different methods available, their working principles, advantages, limitations. I will also cover various electromagnetic and acoustic non-destructive techniques, and I'll also dive a little deeper into the data analysis aspect of it, and then some conclusions. So to begin with, the safety of the bridges are a critical concern for transportation industry, as we all know. And with deteriorating infrastructure, regular assessment become imperative for estimating or extending the service life of the structure. And these assessments could either be durability focused, which may include some concrete testing in addition to some non-destructive testing, or they could be structural in nature, where the primary focus would be load rating calculations. However, more often than not, we do not have access to the original of the as-built drawings, or they are not even available for load rating calculations to be undertaken. And this is where non-destructive testing methods could be used to fill the information gap and reliably load rate the bridge. There are numerous non-destructive techniques in our arsenal which could be potentially used to evaluate the structural integrity of the structure or to probe the structure. But in essence of time, I'll be only focusing today's presentation on 5 techniques. These 5 techniques can be broadly categorized into electromagnetic methods or acoustic methods, wherein the methods like GPR or ground penetrating radar employs electromagnetic waves to interrogate the structure. On the other hand, acoustic methods like impact echo or through tomography, they use sound waves or stress waves for investigation. Let's dive a little deeper into the ground penetrating radar, or which is commonly known as GPR. It's an immensely powerful technique, and it can provide a wide range of information that can be used for load rating calculations. So the GPR technique essentially probes the substructure conditions of the concrete by transmitting a high frequency electromagnetic wave into the structure and detects the energy reflected from an interface between the materials with differing or different electrical properties such as dielectric constant or conductivity. So in context of concrete structures, these interfaces can be a reinforcement concrete interface, or it can be an air concrete interface, or a asphalt or any overlay concrete interface. The greater the contrast in the electrical properties between these two materials, the more energy that is reflected to the surface and the more defined the results are. So as an example, when the GPR unit passes over the metallic object like a reinforcement or a pre-stressed strand, the electromagnetic waves are reflected back to the receiver in the GPR antenna and is graphically manifested as a hyperbola. And this is what a typical GPS scan data looks like for a reinforced concrete structure, with each of the peak or the hyperbola represents a location of the rebar or a pre-stressing strand. GPRs can come in all shapes and sizes, and depending on the feature of interest, the frequency of the electromagnetic waves or the GPR antenna used to probe the structure should be selected. So since the signal penetration and the spatial resolution is dependent on the wave frequency used, selecting a right type of antenna is highly critical. For instance, high frequency GPRs are used to locate shallower features like concrete cover or reinforcing spacing, whereas low frequency GPRs are typically used for investigating fill layers or locating utilities. So typically high frequency antennas have shallower depth of penetration, but they have higher resolution, spatial resolution. And consequently, the low frequency antennas have greater depth of penetration, but they lose out on the resolution for small and near surface targets. And here is a table showing the antenna frequency and the approximate range of penetration and the depth of and the typical application that antenna is used for. And you can see that the higher frequency antennas are used to investigate shallower features like rebar depth or spacing, and maybe like presence of subsurface conduits or something like that. Whereas the low frequency antennas are typically used to detect soil settlements or for utility locations or locating the utilities. But one needs to be careful that these depths of penetration are for ideal conditions. If there is a presence of a highly conductive layer, such as a brackish water table or a steel plate is present in the subsurface, then all the antennas will be limited to that depth of layer, since most of the signal will be reflected from this highly conductive layer due to the sharp change in dielectric constant. So the user need to be cognizant about these factors. So the different pieces of information that can be derived from ground penetrating radar or GPR are concrete cover depths, reinforcement quantity or the layout of the reinforcement. We can also detect number of different reinforcing layers present. We can also probe the thickness values in terms of what is the thickness of, let's say, an asphalt overlay or what is the concrete section thickness. And interestingly, ground penetrating radar also give us the ability to probe the subsurface degradation mechanisms happening. Maybe it can probe into the presence of moisture or presence of delamination or deterioration, which can lead to the attenuation of GPR signals. GPR can also give you an idea into that. So let's talk a little bit about concrete cover first. The concrete cover can be estimated by measuring the distance between the zero line of the data and the peak of the hyperbola as shown in the GPS scan here. However, in some cases, the presence of air gap between the GPR antenna and the surface of the structure could result in the downward shift of the data. And that could lead to inaccurate estimations of the cover depth. And in such cases, there's something called a time zero correction could be required. And here is how the data would look like after the time zero correction. So Depending on the setup being used or what kind of a GPR unit you're using, some of the newer GPR units have ability to autocorrect for this error. So that's one more thing you need to be cognizant about when analyzing the data, the air gap or the time zero correction. And once the cover depth is accurately estimated, the values can be plotted in a 2D heat map. And here is a good example where the cover depth measurements are plotted as heat maps to show a spatial distribution of the areas of the low covers and the areas of the adequate cover. And with this information, you can also calculate the statistics of the percent area which have, like, let's say, low cover than specifications, and the percentage of area which have adequate cover or more than adequate cover. And since the cover depth can significantly affect the load ratings of the structure, these statistics can be a vital piece of information an engineer can have. And in addition to the cover depth information, these heat maps indicate the areas where low cover is present, which are susceptible to moisture ingress or, let's say, chloride attack. That could potentially lead to corrosion of the steel reinforcement in the structure, which effectively contributes to the reduced load-bearing capacity of the structure. So there are multiple information that can be derived from a simple heat map of the cover depths. Next is reinforcement spacing or layout. GPR gives you ability to measure both. If you simply measure the distance between two hyperbolas, you can get the spacing between two reinforcement or two rebars. And this GPS can also shows the bottom surface of the slab. And it also shows, let me highlight this with a pointer here. So GPR gives you ability to detect what is the concrete slab thickness, and also this GPS can also shows a transition from the bottom of the slab to the bottom of the beam. So it was taken on a concrete deck where you could also see the underside of the deck and also a beam that is present on the underside. GPR can also detect the presence of multiple layers of reinforcement. However, the visibility of the deeper mat of the rebar is dependent on what is the rebar spacing for the top mat. And what I mean by that is if the reinforcement spacing in the top mat is tightly spaced, or if the rebar is placed very close to each other, then that might affect the visibility of the second layer of rebar. And in such situations, taking a scan from a different side of the structure or another angle might be of some merit. And I'll go over one such example in subsequent slides. Here is one of the single span bridges owned by Florida Power and Light down in Sarasota, Florida. And the deck on this bridge is supported by pre-stressed I-beams. And as it always happens, we do not have any as-built drawings available. And that's why the owner could not have any information about what is the size, type, or spacing of the reinforcement present in the I-beams. And so for the load rating calculation to be carried out, these three pieces of information about the reinforcement are important and they are needed. So GPS scans were collected on the webs, flanges, and the underside of the I-beams to get a sense of how the rebar is distributed or if there is any presence of the pre-stressed strands. And here is how a GPR scan data looks like. This scan was collected in the horizontal direction from the web of the I-beam, which shows a tight spacing towards the end of the beam, and the rebar is widely spaced, or the shear reinforcement is widely spaced towards the middle of the beam. So that's one information we can get from the horizontal scan. On the right is a GPR scan data collected from the beam underside, which shows a layout of the bottom layer of the pre-stressed strands. However, it says that the second layer of strands was unconfirmed due to the inability of GPR to see through the tight spacing of the bottom layer. However, there is one way to tackle this issue. We did some scans from the side of the beam, side of the bottom flange, which shows that there were two peaks, presence of two peaks in the bottom flange area. And thereby we could confirm the presence of the second layer of pre-stressing strand in this case. So if you get creative with your scans, I would say collect the data on all the sides of the structure to get a comprehensive piece of information regarding the layouts or the spacing. In addition to laying out how the rebar is placed in the structure, it's highly important that we also know what is the size of the reinforcement. It is actually a critical piece of information for the load rating calculation. And that's why it becomes necessary to make the probe openings. You make a small opening, let's say 4" by 6", and then you expose the strand, you take the actual measurements of the strand so that you know the exact size, and then you can always patch it back. So in other words, using a destructive testing, meaning actually or physically measuring the strand diameter, increases the confidence in the load rating calculation. So probe openings, in addition to the GPR scan, can give you an immense amount of information for the calculations. In addition, the data from the non-destructive testing is only as good as the data analysis or the interpretation is. So here is an example which can highlight this point, where these are the two scans from the bottom and the top of the box beams. You see the first layer of the top face scan shows the presence of the reinforcement, whereas the top layer of the bottom face shows the presence of pre-stressed strands. However, when you look at the three peaks at the middle of the pictures you see here, you see three peaks which are common to the top and the bottom faces. And these three peaks can be easily misconstrued or misattributed to the presence of reinforcement. However, if you look closely, these peaks have an opposite signal polarity as compared to the rebar or the strand peaks, where the rebar peak, in terms of the color contrast, it looks like black, white, and black. However, these three peaks look white, black, and then white, similar for the bottom face. So it implies a presence of a different interface when there is a polarity change than a steel concrete interface. And these three peaks in reality correspond to a concrete air interface, which confirmed the presence of sonotube or a precast void in the box beam. So the person analyzing the data should also be cognizant of such nuances in the data analysis. And also, once you have the data, the layout confirmed, then the engineer can always compare it to a standard layout present in the specs or the standards. In addition to cover depths and layout, GPR, as I've already mentioned, GPR can also give you an information about the subsurface degradations by means of amplitude analysis. This is one way of analyzing the GPR data. And the amplitude analysis takes advantage of the fact that GPR signal amplitude can be attenuated because of the presence of subsurface delaminations or presence of moisture. So if the concrete subsurface area has a delamination or a moisture present, then you will get a weaker GPR signal back to the antenna. So therefore, the analysis of reflection amplitudes can provide an insight into the condition of the steel and the quality of the concrete cover. And one good example of such analysis is the Gober Memorial Bridge in Florida. Now, this bridge is a pretty long 22-span bridge with 2 lanes, which is supported by pre-stressed concrete girders. And there is a boat launch marine on the west end of the bridge. And due to the proximity of the marine launch, the bridge deck is constantly exposed to seawater dripping from the boats or canoes that are being driven over the bridge right after the removal from the water. And as a result, the bridge deck and the substructure elements are experiencing deterioration in the forms of delaminations or spalls, and especially on the eastbound lane. So to assess the damage, we did some GPR scans on the deck, and we did amplitude analysis, and the amplitude heat maps were plotted. And as can be seen from the heat map here, the eastbound lane shows a significantly higher proportion of area with poor or fair condition as compared to the west lane, where the majority of the area was in the good condition. And the area of high signal attenuation indicate location of probable concern, indicating potential contamination or deterioration, and this deterioration just could be the high concentration of chlorides or moisture, which could lead to corrosion, or it could be corrosion activity and concrete cracking. The difference between these states cannot be discerned by the GPR, however. The areas are identified by the amplitude analysis, closely overlap the delaminated and the spalled areas identified by the hammer sounding and dragging. So this serves as a double confirmation. So you get some data from the GPR and you verify it with hammer sounding, and then you can be very sure that the delamination or the subsurface defects are present in the concrete. So the relevant data derived from the GPR that can be used for load rating calculation is concrete cover depths, reinforcement layouts, section thicknesses, and areas of deterioration or like delaminations. In addition, we can also probe the overlay thicknesses. If there is an asphalt thickness, asphalt overlay present on the concrete deck, you can also see what's the thickness of the asphalt present there. The next technique, impact echo and pulse velocity, I'll discuss are acoustic methods, which use sound waves or stress waves to probe the concrete. And the same setup is used for impact echo and pulse velocity measurements, where the energy source and the receiver are placed on the concrete surface. However, the impact echo technique analyzes the response wave in the frequency domain, whereas the pulse velocity technique analyzes the wave in the time domain or the velocity domain. The energy source used for either of the technique can be as simple as a ball peen hammer or a steel ball bearing, or it can be as sophisticated as a transducer-induced sound wave or a pulse sent into the concrete. And I'll talk about these instrumentation in the next slide. So in terms of the materials that can be tested, these techniques are versatile, and in impact echo or pulse velocity can be used for the quality assessments of the metals, plastic, wood, or concrete. So it's really versatile techniques. In terms of the instrumentation for these techniques, both techniques have the same setup where we often use steel ball bearings and a pneumatic ball bearing impactor as the energy source. And once the stress signal or acoustic signal is sent into the concrete using an impactor, a piezoceramic sensor array is placed right next to the impactor and is used to probe the response of the structure by detecting the waves traveling through the concrete, which is then processed by the data collection unit, and the data displayed is then analyzed by a technician. So in terms of distinguishing impact echo and pulse velocity techniques, impact echo uses sensor 1 and 2 to analyze the echo response in the frequency domain to evaluate the thicknesses of the concrete, whereas the pulse velocity technique uses sensor 1, 3, and 4 to measure the time taken by the waves to reach the respective sensors to get an idea of the in situ compressive strengths or the modular values of the concrete structure. So when the ball bearing or the BB hits the concrete surface, this is how the stress wave typically would travel. And you see a wave here in the in the video that the wave is being reflected off a horizontal white line, which represents a subsurface crack in the concrete. So when the sound waves travel in the concrete and across the concrete, the sensor is waiting for the wave to pass by. And we are looking for essentially two different kinds of waves. One is a compressional waves which is also called as a primary wave, which travels parallel to the surface. And the second wave we are looking for is a shear wave or a secondary waves, which travels perpendicular to the surface. And this is how the response data looks like on the data acquisition unit, where the left image shows a high frequency signal being read by all the four sensors, and there is no attenuation in all the four channels or all the four sensors, which is indicative of a good quality concrete, whereas the cracked concrete shows a severely attenuated signal and distorted signal on sensors 2, 3, and 4. Furthermore, the cracked concrete sensor 4 on the cracked concrete, the sensor 4 shows a reduced compressional and shear waves velocity as compared to the sound concrete. So although the data analysis of these techniques can be highly nuanced, these are the telltale signs of the presence of a subsurface defects like cracking, voids, or delaminations. So as the name suggests, the impact echo technique uses the resonant frequency of the echo or the reflection of the compressional wave to get the section thicknesses or to detect the presence of the cracks, delaminations, or microcracking. And also, it can give you an idea of the compressive strength of the structure in the thickness direction. On the other hand, the pulse velocity technique analyzes both compressional wave and the shear wave to get an in situ compressive strength of the concrete section and the modular values as well. So in terms of the characterization of the material, pulse velocity gives you a more of a 3D picture of the structure, whereas impact echo gives you more of a 2D or a information about the concrete structure in the thickness direction. And these techniques are really great in estimating the in situ compressive strength of the concrete, where the in situ compressive strengths account for all the dynamic stresses the structure is exposed to, as opposed to the uniaxial loading in the lab testing of the concrete cores. And these estimated compressive strengths, when plotted as heat maps, can give you a spatial distribution of the weak areas, highlighted by the red and the yellows, and the strong areas of the concrete. And these heat maps can serve as a guide for selecting the representative concrete sampling locations. For instance, you can take a few concrete cores from the red areas or the weak areas, and you can sample a few concrete samples from the good areas. So you can decide the location of your concrete cores or powder sample based on the heat maps. Impact echo can reliably measure the thicknesses up to 4 feet. But if you need to measure a higher depth, either we need to increase the sensor spacing, or we can use different techniques such as reflection methods, such as pile length testing, which I'll talk about in subsequent slides. So the relevant information that can be derived from from impact echo or pulse velocity that can be used for load rating is concrete section thicknesses, information about delamination or microcracking, the location as to where they are present in the structure. Whereas pulse velocity can also give you an idea into in situ compressive strength, which takes account for all the dynamic stresses on the concrete. Also, 3D condition assessment of the concrete structure in terms of detection of the microcrack or the assessment of the macro cracks. However, I would say that using impact echo in tandem with GPR would increase the confidence in the data. If you use two techniques to assess the structure, it will give you a higher sense of certainty in terms of the data you're looking at. For example, comparison of the thickness data from impact echo and that obtained from the GPR would serve a double verification, in the sense that we can be sure that the dielectric constant being used in the GPR technique is correct, and the frequencies that are being analyzed in the impact echo measurements can confirm the thicknesses from the GPR unit. So it acts as a double verification. The next acoustic technique is pile length testing, or PLT, which measures the time between the impact and the detected reflection to get the length measurements on the bridge piles or any piles for that matter. But for this technique to work, we either assume a velocity of the material being tested, or we measure the velocity with a known thickness. More often, this technique is also called as pile integrity testing, or PLT. It's the same technique and uses the same concept. So the technique can be used to detect the location of any breaks, splices, or cold joints in the pile. I wouldn't call it a disadvantage, but you need to have access to the top of the pile to take the measurement, top of the side of the pile to take these measurements. And again, these technique is very versatile in terms of it can be used on a wide variety of piles, like drill shaft or friction piles, or even timber piles or like sheet piles. Here are some pictures from various projects where the piling testing is being performed on pipe piles, sheet piles, or timber piles. And one good example of the pile length testing being used on the concrete pile would be US 90 bridge over Aucilla River in Florida. This bridge consists of 12 spans and is supported by 11 pens with 18-inch square precast concrete piles. But the driving depth of these piles was unknown due to the lack of construction as-built drawings. And here is one of the technicians performing the pile length testing on those concrete piles in the picture. You can see a sensor array is being strapped to the concrete surface, the concrete pile. And this can give you an information about the total length of the pile if you know the exact length of the pile above the water, and it can give you an idea of as to what is the total or the entire length of the pile. It can also give you an idea if there is a break in the pile or any subsurface cracking is present. So in terms of relevant information derived from pile length testing for load rating calculations can be total pile length, which is a combination of exposed pile length, which is a measured unit, and embedded pile length. It can also give you an idea, as I'd already mentioned, about the cracks or the splices in the piles. And it can, for the concrete pile specifically, it can tell you if there is any cold joint present and what would be the relative location for that cold joint. And the last acoustic technique which I'll talk about is through tomography, where the energy source or the transmitter and the receiver is placed on the opposite sides of the concrete element. So the access to both sides of the concrete is required. However, for this technique, the concrete section thickness should be known, and that is where the wave velocity traveling through the concrete can be calculated. The through tomography measurements are it's all about taking the measurements in a grid pattern whereby a matrix of measurements can create a 2D slice of the data called a tomogram, wherein all the ray paths you see here from the transmitter to the receiver, every ray path is used to calculate how the tomogram or how the subsurface or internal concrete looks like. And this is a sample tomogram image where you see a lighter shaded zone in the center of the concrete, and that is indicative of presence of a weak zone. It could be due to a void or honeycombing or any delaminations present in the concrete. Tomography can interrogate any questionable questionable internal concrete, and the grid data collected produces a slice shown on the left using the tomogram program. The lighter shades on the center of the slice indicate weak zones, which could be attributed to voids, honeycombing, or delamination of the crackings. However, the lighter shades on the surface, also called as the tiger strips, indicate the data gaps from this technique, and those are not necessarily the weak zones on the surface. These data gaps are attributed to the areas between the sensor location where no data was collected. These data gaps can easily be filled by performing surface pulse velocity measurements, and you can get a whole set of data. Another way to deal with the surface data gaps is to perform the measurement in finer grid spacing. And one good example of application for through tomography is Pensacola Bay Bridge in Florida, where the owner was concerned that the delays in the concrete pour in Pier 51 may have caused consolidation issues. So to assess the concrete condition and to identify the areas of consolidation issues, we performed through tomography in a grid pattern. We took the measurements in the grid pattern. And you can see in the images here that both the access to both the sides is needed to make sure that the transmitter is placed on one side of the pile, whereas the receiver is placed on the other side of the pier of the pile. And the tomogram data collected is divided into numerous slices, and here are some slices of the data using the tomogram. The presence of the void or the weak zones can be confirmed, and their locations could be identified. And on this project, it was established that the surface of the pier had competent concrete, so there was no need for the technicians to fill the data gaps on the surface. So if you are able to confirm that the surface is competent, then you don't necessarily have to fill those data gaps. And you see this color scale which is being used to plot the heat maps. The reds are an indication of poor consolidation or interconnected discontinuities or like large segregations, whereas the good area is like a solid concrete, and then there is an intermediate zone which could be indication of high entrapment zones or minor cracking or minor segregation. The through tomography also equips us with the ability to perform the time study on the structure to track the deterioration over time, since this technique provides an easy visual guide as compared to other techniques such as impact echo or pulse velocity. In addition, through tomography can also be used to check the effectiveness of the repair process. And a good example of this could be an I-95 interchange in Providence, Rhode Island, where the crack injections were undertaken for the pier caps and the columns, and the tomography data was collected before and after the epoxy injections. And this is how the tomogram looks before the epoxy injections were made. And this is after the epoxy injections were made. And the difference is clear as night and day, where the weak zones are significantly minimized, if not eliminated, as suggested by the increased strength. So time study, and you can also check the effectiveness of the repair process. So in terms of the relevant information that can be derived from through tomography is in situ compressive strengths. We can 2D map the weak zones, voids or honeycombing. We can also get an idea into the presence of air pockets. So in conclusion, there are numerous tools in industry which can be used to probe the data or like to probe the structure. But you need to know what you're looking for or the feature of interest you're looking for. And then to summarize all the techniques, ground penetrating radar can give you an idea into the depths and the layout of the reinforcement, whereas impact echo or pulse velocity can probe the section thicknesses or in situ compressive strengths, whereas pile length testing can be effectively used for length measurements, and through tomography can be used to plot the bulk defect or assess the internal concrete. So in conclusion, I would like to leave you guys with a thought that one technique will not give you a complete picture of the structure. Using combination of two or more techniques will highly increase the confidence in the data you are getting and the characterization techniques you're using to probe the structure. And that's it from my side. Thank you.
Awesome, great presentation, Pratik.
Thank you, Ben.
We are now in our Q&A section, so get your questions in now. We'll start firing those at Pratik, and he's going to use his big brain over there to answer them, as all the experience he has in doing this. So I'm going to start him off with a question from Matthew. Is there any non-destructive technology out there that can discern between conventional rebar and pre-stressing cables?
GPR can do that if you know what you're looking at. So typically, the peaks you see in the GPR technique, like the hyperbolas you see in the GPR technique, those can be conclusive enough to discern between the pre-stressed strand or a grouted post-tension duct or a rebar. Just the width of the peak and the thickness of the peak will be able to tell you like if the GPR, if the strands are present or the rebar is present. But yes, in addition to GPR, if you use another technique to confirm your measurements, then it gives you more confidence in the GPR technique. So yes, GPR can be used. So yes, to answer Matthew's question, yes, there is a technique and GPR is one of them.
Awesome. From Solomon, can you determine if reinforcement has been corroded by the data collected by GPR?
The level of corrosion on the reinforcement cannot be detected by GPR, but there is another non-destructive testing called as corrosion potential surveys, which can easily tell you like to what extent the rebar has corroded or what is the probability of active corrosion happening in the concrete. So no, the GPR cannot tell you like how much corrosion has happened or what is the rate of corrosion, but another non-destructive testing, corrosion potential surveys or half cell, what we call it, it can be used to assess the level of corrosion or like the corrosion activity in the concrete. So yeah, but that was an excellent question. Yes.
So you mentioned in the impact echo and pulse velocity that you can get the in situ compressive strengths.
Yeah.
How well does that measurement relate to the in-lab compressive strength when you test those concrete cores?
I see. Oh, that's a really nice question. So if you're talking about the concrete cores taken from the structure, whereas and then subjecting it to the compressive strength test in the labs, whereas impact echo you're doing in situ, there is a really good correlation. So for older structures, impact echo or pulse velocity typically tends to underestimate the compressive strength by, let's say, 500 psi or so. Whereas for newer structure, it it has almost like 95 to 98% of the correlation as compared to the in-lab testing. So the results are very comparable, but at the same time, I would say impact echo probes into the dynamic stresses which are actually present on the structure, whereas when you take the core out, there are no stresses being applied except for the stresses applied by the machine to perform the compressive strength. But to answer your question, there is a good correlation between the in-lab testing of the concrete cores and the impact echo data received from the field.
So you mentioned, so this is a question from John. You mentioned that you can't get the size of rebar using GPR. Is there any non-destructive technique that could give you an estimate of a rebar size?
Yeah, they have cover meters present where you place it on the concrete, and you as long as you place it right over the concrete, over the rebar location, it can estimate what would be the probable size of the rebar. So yes, we have cover meters. I think those are ProSec cover meters, so you can use them to get an approximate idea of the rebar size. Yes, you can do that, but I would say verifying it using the opening or looking at the drawings would help. But in most cases, the drawings are not available. So especially for the load ratings, making an opening is of high value.
Awesome. Yeah, we're getting a lot of good questions here. Another one from Megan. Is there an ideal combination of techniques, in your opinion, that would provide the best picture of the inside of a structure?
It depends on what you're looking for. If you're looking for corrosion activity, like the level of corrosion, then corrosion potential surveys would be sufficient enough. But if you're looking into mapping the weak zones, then maybe using a hammer sounding plus impact echo and GPR data would give you a really good idea as to what areas could be delaminated or voids could be present in the subsurface. So it all depends on what you're looking for.
We're getting a few questions here from some anonymous people. So if those want to reply to their comments with their name, then Pratik will be able to reach out. But I'll fire one of these from anonymous number 1. What are the challenges of a concrete deck overlay when it comes to using GPR? Is it possible that you can still get readings with it, or how does that affect your readings with an asphalt overlay?
Really nice question. So one thing to be mindful about while analyzing the asphalt overlays or any overlays for that matter is when the GPR wave or the electromagnetic wave passes through the asphalt layer and then through the concrete layer, you can get a thickness, but you need to make sure that in the data processing, you account for a correct dielectric constant, because the concrete dielectric constant is very different than asphalt dielectric constant. So if you use a concrete dielectric constant to measure the asphalt thicknesses, that might give you an inaccurate measure of the thickness. So you need to be very cognizant about the fact that these two materials have different dielectric constant, and you can look up in the literature to see what is the correct dielectric constant for the asphalt overlays to measure to get the exact thickness of the layers.
From anonymous number 2, while the frequencies give different information, does change. Sorry, let me reread that. How does the wave type give different information, i.e. sawtooth waves versus spine waves versus step waves, etc.?
That's a good question. Different wave. So as long as we have the baseline as to what the good concrete looks like, we can always compare different kinds of waves into and compare it with the baseline. But it all depends on when. So in terms of pulse velocity, let's say pulse velocity technique, it all depends on when the waves. What is the time taken by the wave to come to the receiver or the sensor array? So based on what kind of a wave, and you need to be really experienced in analyzing the data, different waveforms can give you different information as the question poses. But we'll have to get into like a finer comb with to see what each wave talks about. But it's all subjective depending on what you're looking at, what is the thickness of the structure, what are the possible deterioration mechanisms of present in the structure. So I wouldn't comment on what specific waveform represent in terms of defect mapping, because the exact same waveform can mean two different things in two different structures. So it's all relative, I would say. But I can look up on that, and I can always get back to have a better answer prepared for this. Yes.
Yeah, that one was anonymous, so hopefully they'll reply back. But yeah, it's a good point that the data is only as good as the analysis, and
right.
Having the most context and experience when you're analyzing that and interpreting it is hugely important.
Yeah.
Can you measure levels of corrosion in steel type bridges like steel girders, steel trusses, etc.?
Levels of corrosion potential surveys can do that. Obviously, that level of corrosion potential surveys can be performed on the concrete, but they don't necessarily relate to the load ratings. But that's an excellent technique which can give you an idea as to how is the spatial distribution of the corrosion hotspots or passive areas over the structure. But for steel girders and what was the other element you mentioned, Ben?
It was a steel girders and steel trusses.
Yeah, you can do those, but typically for open steel members, we tend to perform section loss measurements where you polish the surface, you see what is the remaining section of the steel member, and then you compare it with the standard sizes and you calculate the percentage section loss that has happened over a period of time, and that can give you an idea of the corrosion rates of that steel member. So the only way to assess, one of the way to assess the corrosion rates of the steel members, like without the concrete overlay, would be to have section loss analysis.
Right. Yeah. From Robert, he says it's related to masonry, especially with arch bridges. Are there any techniques that are well suited to investigations with masonry? Can you get the strengths of that masonry, or get potential areas of ring separation?
Impact echo can give you an idea into that, like especially with the masonry units. Impact echo or like impact echo in tandem with GPR can give you an idea as to if there are any defects or if there is any separation or delamination present in the subsurface. So yes, impact echo can be used in those cases. Because essentially we are relying on the sound wave to travel through the medium, and it can, as I had mentioned earlier, like impact echo is very versatile in terms of the material it can characterize. So impact echo or pulse velocity or any acoustic method, as long as the sound wave travels through the medium and comes back, we can assess those. Yes.
Can these acoustic techniques be used to investigate bonded post-tension systems?
Yes, that's an excellent question. So we often use impact echo technique to assess if the bonded or the grouted post-tension ducts are filled, if there are any lens voids present, or if there is any grouting defect present in the ducts. So if the sound waves can travel, or if depending on the response of the bonded post-tension or the metal ducts, we can see if there are any lens void presence, or if there is any like breakage in the duct or any defects in the duct present. But what we typically do is once we perform the impact echo measurements, we identify the locations where there could be a potential issue present. And then we do some openings like destructive testing, and we use borescope to look into the ducts. That will give you a more comprehensive idea as to what you're looking at.
Great answer. Yeah. These questions are really flying in here. Hopefully we can get through them, but let's see here from Datani. Could any of the techniques discussed today or any other non-destructive techniques be used to know the condition of post-tensioning strands and ducts in concrete for corrosion or voids?
For corrosion or void, you need a visual assessment. Like you need to make some openings and for borescope. But as I answered the previous question, impact echo or can give you an idea as to if there are any potential defects in the duct present. And then once you have assessed like what are the potential areas of defects, you can just make a small drill hole, reach the duct, open the duct, and then you can use borescopes to inspect if there is any breakage in the strand or any grouting defects or any corrosion on the ducts. So yeah. But
okay.
Corrosion assessment would need a visual means to confirm.
Right. From John, the color map earlier in the presentation showed concrete cover in half-inch increments. Can more accurate or smaller cover increments be found in mapping results? Like half-inch is still coarse, and sometimes that extra or lack of cover can make the difference in areas of very low cover.
Right. So the cover depth map is one way to show the data, but we can always give the client the exact number. Like if the cover depth, we can go up to like second decimals, but that is a more visual cue. Like if you plot it as a what do you call it, the heat maps. But if the client needs the exact values assessed on the structure, then we can also give them. But there is a good sense of accuracy in the GPR cover depth. So yes, you can be really accurate with the cover depth measurements, and even with the rebar layout. Yeah.
Excellent. Oliver is asking, is there a non-destructive testing method that can estimate the tension present in a pre-stressed cable?
If there is, I'm not aware. I'm sorry, but I'm not aware of the technique which can non-destructively tell you like what is the strain present or like what is the tension level present in the strand. But I can look up on that and I can always reach back. But as of now, I'm not aware of the technique which can give you the actual strain present non-destructively. I would assume that you would need access to the strand to see what's the tensioning available at that strand.
We've got a long one here from Rakesh. Can we use GPR with any other acoustic technique to develop full reinforcement details for reinforced concrete half joint, which is deeper than 600 millimeters or more, including fully developing anchorage depths of reinforcement in these areas?
So if you want to look deeper, I would recommend going for a lower frequency GPR antenna that will give you information about a deeper feature of interest. In addition, if it's possible to have access to like the top and the bottom side of the joints, it will give you more comprehensive information. So you can use impact echo with a low frequency GPR to assess the deeper features in the joints. Yeah.
Michael asks, is there any technology that can determine how hard the structure is working without calculations or analysis? Like, would you be able to measure the compression of the concrete itself or the stresses that it might be under?
Oh, so does he mean by, so impact echo can give you in situ compressive strength that accounts for all the stresses that are being put on the structure. And I think that can be a good enough indication as to where the weak zones are, because if you take a core out of weak zone, then those stresses are removed. So to answer it simply, impact echo is the technique which can give you a dynamic stresses. And then if you combine, you can have the thickness measurements as well to see like how the section looks like and what could be the potential stresses. But in terms of just analyzing the dynamic stresses present, impact echo is the way to go, I feel.
I don't think we're going to be able to. These questions are really coming in fast, but what does the final data look like for the acoustic methods?
For the acoustic methods, the final data can be a string of numbers depending on what the client needs. If they want each and every value that was measured on the grid pattern, we can give them a string of numbers. Or if they want a visual cue, we can give them heat maps. So you can, depending on what you need. I think heat map are a better representation or a visual representation of how the structure looks like. And whereas if the client wants to go in much details, like as to what did each location correspond to in terms of the compressive strength carried or the thickness measurements, then we can also give them the string of numbers and we can do it either way.
Okay, so I think we're going to do maybe 2 more questions, and then we'll have to pass these on to Pratik to answer in the after show here. Yeah. But in the UK, a popular bridge construction is inverted precast T bridge beams with either a slab or a solid mass concrete infill. The pre-stressed strand is often debonded along the beam length, and possibly the beam's edge might be the same size but have different strand patterns. Is there a non-destructive technique to identify the debonding zones?
This is a very specific question regarding the project. If I have more details onto this project, and I can reach out to the person who asked this, but if we have more data on the structure, we can definitely look into those. But again, impact echo and GPR could give you an idea as to if there are any debonding, like it can spatially locate the debonded zones in those inverted beams, yes. But right. If you send me more details, I can just always more than happy to look into that, yes.
Yeah, that one was from Paul. So we'll be able to get you his information and you can connect after the show. Last question, how accurate is pile testing?
Oh, pile testing can be really accurate if we are testing a homogeneous material. For instance, if we are testing steel piles, then the measurements can be really accurate. But if we are testing a non-homogeneous material, let's say timber or concrete, then the accuracy goes down. Not to the extent that it will give you some inaccurate results, but there is a good correlation between the homogeneity of the material and the accuracy of the measurements. So steel, amazing results. There is a slightly reduced confidence, but you get really close to the actual values for the concrete and timber piles, yes.
Excellent answer. So I'm going to cut us off there. We'll get the rest of these questions to Pratik, and he'll get back to you guys about those. But if you have any more, you weren't able to get them in, or you think of some later, on screen is Pratik's information. You can find his phone and his email there. So he's more than happy to answer any of your questions about the things that his company BCS does, their non-destructive testing and analysis. The presentation will be uploaded to our website, as we mentioned at the beginning. You can also find our the slides that Pratik was using here today as well, and you'll be able to register for next month's webinar. And I think that is the end of the show. Thanks, Pratik, for that awesome presentation.
Thank you, Ben, and thank you everyone for attending the webinar.
And let's get out there and save some structures.